as we go along, okay, without looking ahead, okay, without using human operators, without any confusion. You have to design a code, okay, that has no confusion, and also, preferably, do not need to look ahead, right? If you have to wait, look ahead, then decode, and it might not be as good as a code that you can decipher instantly, okay, if possible. Okay, so these are the things that we're going to take a look next in the next few slides. And there are also algorithmic issues, right? Is there a systematic design? Also, is there a simple, fast encoding, decoding algorithm, automatic, okay, that the computer can, that we can easily implement on a computer? So I have a few examples here of various type of code for this type of data. Okay. My data has 5 symbols, A, B, C, D, E. Okay? A, B, C, D, E. With probability being 1/2, 1/4, 1/8, 1/16, 1/16. The total, if you sum up all the probability, you have to make sure that it's 1. Okay? That's the first thing that you should always get when you do your computer exercise or written exercise. And how do I come up with this H number? What is H? H is the entropy, right? And we just simply plug in the formulas, okay? Just plug these into the formulas. We have a formula. You come up with 30/16. So which means you take slightly less than 2 bits, okay, to encode this source. And that is the best that we can do, given that all of these guys do not have any memory, like have no relationship, okay, between themselves, okay? Independent events. Now, if I use fixed length code, okay, 5 is above 4, so I'm forced to use 3 bits. And there are a few guys that extra, right? Because with 3 I can represent 8 symbols, but I only have 5, so I'm throwing 3 guys away, and that's why you're paying for it. Okay? You are way above entropy, you're very wasteful. Okay? You're throwing a lot of your bandwidth away using fixed length code. Okay? But then let's take a look at other codes, and let's see which one is good and which one will lead to trouble. Okay, so maybe the first thing that we should look is the average length. Okay, and you notice that hey, this guy is pretty good. Actually this is the best, right? Because we're able to match the entropy. That's as good as you can do it. This guy doesn't seem to be on the same level of performance. But what about which one do you think has confusion when decoding? 4 has confusion. Why?
1.
Yeah, when I receive 1. Right. Then I don't know, should I decode it as D or I should wait and decode it as E. Okay, so you already mentioned prefix, which is exactly what the keyword that I'm looking for. Okay, no code can be a prefix of the other, because that will always lead to confusion. Is that true? Okay, we don't need fancy mathematical theorem to show that, right? It's very intuitive. In this case, since it's sequential. Okay, so this violates the prefix code. And what about, okay, so this is how I compute the entropy. And for the code 1, this is how I get this 31/16 numbers. Okay, the expected length is the comparable number to the entropy. Okay, this is on average. How many bits are you going to take if you use this code? Okay, now A happens half of the time. Every time A happens, you spend 1 bit. Okay? Every time B happens, B appears, you spend 2 bits, right? So on and so forth. So every time C appears, you spend 3 bits, 4 bits here, 5 bits there. So it comes out to 31/16 bits per symbol. This is pretty good, but you are not as close to, you're off a little bit, okay? Now, next, let's investigate uniquely decodable. Uniquely decodable means there's no confusion in the decoding process. Okay? Uniquely decodable, and you can easily verify that 1, 2, 3 doesn't have any confusion in the decoding process. However, take a look at code 1 and code 2. Now, can you tell me which one is better? Just between 1 and 2. Which one is better? 1 is better. Why? What's wrong with 2?
When you receive one,
is there a confusion in 2?
If you receive the one request,
This is the key. Turns out that code 3 is Huffman code. Okay? So instantaneous is 1 and 3. We don't need to look ahead. We can just decode now. Okay? And the prefix condition is that which combine these two properties here, instantaneous and uniquely decodable. That say no code word should be a prefix of another. So that's avoid both uniquely decodable and instantaneous call. Okay. So the first code that satisfies the prefix condition that actually works very well is Shannon-Fano code. Okay, and this comes up very shortly after Shannon published this entropy formula. Okay, and he automatically thinks of the next step. Okay, how do I design such a code to match my entropy? Okay, so he proposes. The algorithm is actually very simple, right? You should line up your symbols with probability of occurrence like this, okay? And then you divide the symbols into two groups so that both have roughly the same combined probability. Because you need to assign 1 and 0 to each of the groups, okay? So the first thing that I would do in this case, where should I draw the line? Between A and B, or between B and C, or between C and D? Probably between B and C, right? Because 0.35 plus 0.17 is roughly, give you roughly the closest to half and half, right? So the first line I'm going to draw is this, and I'm going to assign 0 to all the one upstairs and 1 to all the one downstairs. Okay? So guess what we will do next? We repeat until we resolve all the symbols. Okay? So the next step is to draw a line between A and B. This is trivial. So assign 0 for upstairs, 1 for downstairs. We're done with these two guys. But then I need to draw 2 more lines for this group. Okay? And in this case, I probably first draw a line between C and D. Assign 0 for upstairs, 1 for downstairs, and then draw the last line here. And that's it. These are the code words. And you can easily see that this construction never breaks the prefix rule because of the way we assign things by group. Okay? You can never have a code word being a prefix of the other. Okay? Because of the way we do the assignment. Okay? So this is called Shannon-Fano code, and it's top-down algorithm. You start at the top, and you start to resolve all the symbols until you're done. Okay? And for this case, the average code word length will turn out to be 2.31 bits per symbol. And that's because when A appears, you spend 2 bits. When B appears, you spend another 2. When D appears, you spend 3 bits, so on and so forth. And this is the on average. Okay? So this is 2.31. And if we quickly go to MATLAB or something to compute the entropy, you come up with 2.23. So as you can see, there's some, okay, it's not that close, okay? There's some redundancy, okay? And this is a good construction, but Shannon struggled with it. Both Shannon and Fano, at that time, they're teaching at MIT. Okay, they work together on this problem, and they struggle with this. They don't know how to show the optimality of their construction, or they know that their code is suboptimal, but they don't know how to come up with anything better, and there's nothing they can